So up here we have all the libraries that we included to make this work. I went a little overboard trying to make it work the first time. Then right here we've defined the buffer sizes through macros for the memory allocation process. And we're going to jump into debugging this program real quick. And right here we're about to start allocating memory for each char pointer in the heap. We're going to continue. Buff1 R1 just got assigned. Buff2 R1 just got assigned. But then right here, Buff2 R1 is about to get freed, so the memory address won't contain that anymore. And we'll illustrate that right here when we assign Buff2 R2. And it'll have the same address that Buff2 R1 had. So obviously Buff2 R1 was freed and Buff2 R2 was then assigned to the same memory address. And then we go to string copy after Buff3 R2 gets assigned. Notably, it's different sizes due to the difference in buffer sizes up here. And then when we try to perform the string copy function, we get a segmentation fault down here. And that is due to Buff2 R1 not actually being anywhere. Right here we have a program, and as you can see, it has a variable int I that has been unassigned, and then it also has a pointer p that's also of type int. And we're going to debug this, and it's going to iterate through a for loop that will go until I is greater than 100. And as you can see right here, I has been assigned an indeterminate value because it hasn't been assigned a value, and p is at value 0 address. And we're going to iterate through this real quick. And as you can see, since the for loop started at I equals 0, variable I right here, the value is 0. And right here, the int p is going to be allocated memory of size int onto the heap. And then we're going to continue. And that's the address of what it was allocated. And then right here, the pointer for p is going to be assigned to I, and so it's going to be reassigned, as we can see here. And so p is going to be allocated more memory. And as you can see, the memory address just changed there. And it's going to keep happening. Now it's at 50, 70, and it'll keep going until it reaches 100 and just keep getting reassigned over and over and over again and allocated more memory. Alright. Okay, so right here we have a program that we're going to run through with the debugger, and the question on the test is, in which memory segments are the variables located? And so right here we're just going to start, and we're going to show right here that a pointer p of type int is equal to the plus function right here with the arguments 1 and 2, and the address is undefined at this point. And then we go right here into the function that was called. As you can see, it goes onto the stack frame, and the stack frame right here is kind of counterintuitive because I think it should be switched, but it still goes from high to low memory, so it's still right. And right here we can see that the p is getting allocated memory on the stack size of int, and the address pointing to the heap is going to go on the stack. And as you can see right here, when we iterate through that, that is the value. And then right here, if we're wondering what happened to our arguments 1 and 2, then we're going to go down here and type in the call info frame, and we're going to see that right here, this is in the stack under arguments. 1, A equals 1, B equals 2, and it's under the argue list. And then our locals are stored right there. The previous frame stack pointer is right there. And so that's pretty neat. And then we're going to see right here that A plus B is P. It's going to return P. And then it's going to print what P is pointing at in the heap. And that's 3. And then we're going to free up the memory on the heap where P is. So right here we have a pretty similar piece of code as the last problem, but on this one we're asked to draw the function stack frame for the following C functions. So what I'm going to do here is I'm kind of going to give a play-by-play on what's happening in the stack as we go through this. So as we go right here, we can see that the pointer P is equal to this function is being called, and the arguments 1 and 2 are getting sent. But first, when you call the main, the arguments in the parameters will be pushed onto the stack first, and then it'll push the return address onto the stack. After that, it'll save the current base pointer and then copy the stack pointer to the base pointer. And once P is pushed on, as well as these 2 arguments, then we move over to plus. But actually, real quick, let's go ahead and take a look at what's going on in this frame. It shows we're looking at previous stack pointers. It's showing the argument list right here, like I said. And so not much going on just yet, but we're going to continue. And once again, we can see that int C equals AB was called, and A is equal to 1, and B is equal to 2. And as you know, C will get the return address will get pushed, and then the arguments will get pushed, and then int C will be pushed. And then let's take a look at this. And so, like I said, we have the previous frame stack pointer right there, and then we have our argument list. A equals 1, B equals 2, and it's showing what frame it was called by. And so that's what I'll return. And then we're gonna keep iterating through this. It's gonna return right here. Generally the same as before. And then we're going to return, and right here, of course, it's going to print. So right here, we have a program that's going to set a pointer of type P, or a pointer P of type int equal to the plus function, and pass the arguments 1 and 2. And as you see right here, P's been allotted an address on the stack. And then once we continue, we'll see that now we're on the plus stack frame, and int C is a local variable. And once we iterate through this, we'll see that int A 1 and B 2 is going to add, and C will be set to 3 over here. And then when we return C, we're going to be returning a local variable address, which is going to cause a problem. which we'll see right here. When we continue and we try to print, let's see, we get a segmentation fault. So we're going to say that this program is not safe. And then right here we have a similar program, but some minor differences. And we're going to start, same basic idea. Pointer P type int has been allotted address on this stack, and then we're going to continue. And one of the main differences right here is that there's going to be memory allocated size event on the heap for pointer P, and so the address in the stack is going to point to this. It's going to be a reference to this. As we can see, this is the address that it's pointing to. And so we're going to continue through this. And now it's going to return P. And right here, when we do printf, there will be no segmentation fault because we're printing the value that this is pointing at. And we're going to continue. As you can see down here, right here, it did print 3. And then one of the biggest things that makes this code safe is that we're going to free the space that P was occupying. And there we go. And we've freed it. We've exited normally. And so overall, we're going to say this is the safer program. So right here we have a statically declared variable in A, and then following that we're going to print the address of A. And since I don't know how to write a script on online GDB to make this run multiple times, we're just going to run it quite a few times and copy the address into Notepad to compare them. And as we can see, the address for NA, which we might expect to be the same every time we run it, is actually being randomized. So the memory address is harder to pinpoint.